And really, there's lots of things in biology you can view as a networks. So you might want to look at the spread of disease up in the corner there. Who gave who the disease? Who did they then pass it on to? It's kind of networking it. You might be able to say, well, actually, I want to look at protein families. In fact, actually, biolayout was first developed to look at protein similarities, that you actually having calculated a matrix of similarities. How do you look at it? Well, the only way to look at it really is as a network. And protein, and I think probably where I first became aware of networks and their use in biology was where people started doing yeast 2 hybrid studies, and they would measure which protein interacted with which protein, and they would get all of these answers between bait and prey. And again, the only way you could show or think about this data was as a network, because that protein interacted with that one and that one and that one then. And you've got these great hairballs, which everybody was amazed about when they first came out 15 years ago. Oh, meaning of life, and there was lots of nonsense talked about them and how they are scale-free in nature. And we can, again, we'll pass on that. So anyway, point is, it's nice thing about networks is you can take a lot of data and you can view it as a very visual representation, and a lot of things are networks by their very nature. Let's say the social interaction network, everybody kind of understands that you have friends and they have friends. But biology can be viewed in this way, and that's what we've been, I suppose, exploring for the last 10 years or more. So into the kind of expression domain, which is what we are going to be looking at, and how we have taken a view of looking at this type of data. So this, some of you I'm sure have seen this before. I guess when we think about this now, it's kind of only in retrospect I understand what we tried to do. So we had a vague idea as wouldn't it be cool to look at expression data as a network, but without really thinking it through, we started on it. But this is the kind of more considered view of what we're actually doing. So if we consider that all data looks a bit like this, that what we are looking at is some unit of measure, and that we have samples of it. We have different samples. Now, those samples could be different patients, data collected from different patients. They could be time. Okay, LPS time course is a time course with replicates. So whatever it is, all data of this nature is essentially a set of values that go up and down over a range of samples. And if you think about it like that, we can treat it all in exactly the same way. And the way that we do it is actually we calculate a relationship matrix called a Pearson correlation. So that's about the only maths that you'll see today, which is the Pearson correlation matrix. And the great thing about what a Pearson does is it looks at each one of these lines and says how similar are they, and if they're really similar in terms of their ups and downs, I'm going to give it a score of 1. And if it's really almost anti-correlated, I'm going to give it a score of -1. And any two lines kind of like this, that might get a 0.3. Okay, it's somewhere in the middle. They're not really correlated, but they may share some things. Well, maybe they're more anti-correlated than correlated. It may get a -0.3. Point is, there's not a strong relationship between these two things. And whilst you can calculate this for one pair, what we're actually doing is calculating for every pair of numbers. Okay. The other thing just to say about this matrix, it doesn't even have to be numerical data, it can be binary data. So you can actually look at yes-no answers. And if you look at a questionnaire, as I have done a few times, then actually what you're really looking at is a series of yes-nos, and you can treat those similarly as a matrix and look at them like that. The point is that when you do this kind of calculation, one, it's very big, but the second thing is actually the chance of two things being related purely by chance is statistical improbability when the data set becomes large, okay? Because actually, if you have 100 samples here, or even 20, the chance of any two things being purely related, so what we have done and what other people have done, if you like, the null hypothesis for this type of data is that you assume it's all random, okay? And if you take a set of numbers like that and you randomize them, you keep all the numbers the same, but you just shuffle them about, then what you'd expect is a distribution of data like that. So if you take, if you like, your null hypothesis for data is it's all random crap, then essentially what you'd get is a distribution pretty much around 0 over a large data set. So the chance of any two things being related purely by chance is very small. We calculated this for one data set, and I think at a 0.7 correlation, it was 2 times 10 to the minus 5, okay? That any two things should be related. But actually what we're looking in these type of data is not for just two things being related, but for clusters of things to be related. So chance of two things being related is very small. Chance of anything being related as a cluster is actually a statistical improbability. So what we are doing in terms of biolayout is we're making this very big calculation, and then we're only saving the top correlations, maybe the 0.1%, 0.5%, depends on the data. So what we are actually looking at is all of those relationships which are statistically improbable, and we're looking at them and saying, why do they exist? The other thing to mention here then is that the larger... Good morning. Is there any more seats? Is there one at the back? Okay, good. So the other thing to mention here is the more samples that you have, the more unlikely things are related by chance. So when Claire first offered me 2 samples to put into biolayout, I said, well, actually, you're missing the point. The bigger the data is, the better this works. In fact, if you've got just 2 samples, as we'll come on to later, you don't need biolayout, okay? So what we do then is, once having made this cutoff value, we have entities, which is a node. I guess we haven't talked about nodes and edges yet, but a node in this case represents a measurement from this data set. And what you are doing is plotting the relationships of any one of those measurements to other measurements, okay? So this guy here, thick and red, is a strong relationship to this guy, but to a lesser extent, it's also related to this guy. So it's really just a correlation of correlations, or a network of correlations between things. So it's called a weighted non-directional graph. So weighted because the edge has a weight, so that we understand that two things are related more highly, so they'd have a 0.9 than something that was related 0.7. So that edge is not just, it's not like I phoned you, that would be a solid relationship. It has a weight to the edge, and that it's non-directional. So what I mean by that, so in a social interaction network, you may be my friend, but I might not be yours, or vice versa. So that relationship is not necessarily reciprocated. In a case where you're actually just asking, are they related, there is no direction to it. Okay? Make sense? Stop. Because if you don't get this bit, you don't get the rest of it. So if that's all clear, then I'll carry on.